So let's talk about what can go wrong in hypothesis testing and how to avoid this, or at least make this risk of doing something wrong as small as possible. Let's talk about lake. Let's talk about lake, and let's pretend that we would like to know if this lake is contaminated or not. But in this case, the contamination, we will assess contamination as an amount of different forms of nitrogen. In particular, it's amount of ammonia. So this is how ammonia looks like. And if you look into different environmental standards, in different countries, of course, they vary. But we can say that in many countries, the limit is 20 milligrams per liter of total ammonia nitrogen. Okay, so that's how much of nitrogen you have in form of ammonia. Okay, and then if it exceeds 30 milligrams per liter, usually some actions might be taken, for example, the cleaning of the lake. So strictly speaking, you have two possibilities. Either your null hypothesis is true, and in my case, null hypothesis is lake is not contaminated. So it means that average total ammonia nitrogen is equal or below 20, so it does not exceed 20. And then you can see in this particular situation, the null hypothesis is true. This is the reality, and this is my test, right? So you can see that the reality and test are almost identical in this particular case. So lake is not contaminated indeed. So it means that if I accept H0, if I accept null hypothesis, this will be something good, right? So this is something desirable, so to speak. But if I reject it, then it's a bad situation, because in this case, I will initiate cleaning of the lake, which is not contaminated. So I will spend or even waste resources, money, human resources, and so on. Okay. So in this situation, when null hypothesis is indeed true, the accepting of null hypothesis is a correct decision, and rejecting null hypothesis is a wrong decision. But it can be also a situation where null hypothesis is false. So lake is contaminated. So again, I test that it's 20 or less, but in fact, it's 22. So it is contaminated. I need to initiate the procedure of cleaning. So in this case, null hypothesis is false. And in this case, accepting null hypothesis will be a wrong decision, and rejecting null hypothesis will be a good decision, right? So what is good and what is bad depends on the situation, but the problem is you never know the reality. So you never know if indeed your null hypothesis is true or not. It's impossible to know it. So what to do? Well, first of all, let's generalize this a little bit, right? The situation when you reject null hypothesis and null hypothesis is correct, we call this situation as type 1 error. Situation when you accept null hypothesis but null hypothesis is wrong, we call it type 2 error. In this case, I have, of course, this lake contaminated, lake is not contaminated, but in fact, it should be H0 is true and H0 is false. Okay. So strictly speaking, these are all possible outcomes of your experiment. You either accept the correct null hypothesis, that's a good decision. You reject incorrect null hypothesis, this is also a good decision. But you can also make two types of errors. You can accept the incorrect null hypothesis, that's type 2 error, or you can reject the correct null hypothesis. This is type 1 error. Again, the problem is that you don't know in advance if it's correct null hypothesis or incorrect null hypothesis. You never know it. So therefore, the only chance you have is to set up your experiments and set up your test to make both risks for both types of error, as small as possible. And it's doable. So let's discuss that. First of all, let me show you these two situations again, but in a slightly different way. So this is the plot you have seen before, right? Here, null hypothesis is true. And look, this plot shows you what happens if you take one glass of water from this lake. So if you take one glass of water from this lake, the concentration of total ammonia nitrogen in this glass can be here, can be here, can be here, can be here, can be here. So it's a pretty big variation, as you can see. But if we take, for example, 10 glasses of water from this lake and compute average, then average will vary within a very narrow range, at least much narrower than this one, right? Because you remember that the variation of the average, it's a sigma over square root of n, while variation of the real values, it's sigma, right? So if you take 10 glasses of water, your variation will be like almost more than 3 times smaller. And this is what we are interested in. We are interested in average concentration, right? Similar, when null hypothesis is false, you can see that In this situation, you can see that the reality and the test are highly overlapping because the difference is very small and the variation is the same. However, if you look at the average variation, so this is the variation of average values, you can see that the overlapping is smaller than we have here. And this is exactly what we are interested in. We are interested in distinguishing average values, not distinguishing the total values, right? So we will be working with average values. Now let's take case number 1, and that's where the null hypothesis is true. In our case, if null hypothesis is true, it means lake is not contaminated. And then you can see that, okay, so we have average 19.9, it's the blue plot. Average 20, it's the black plot. Black plot is what we test. This is our assumption, our default assumption. Blue plot is a reality, but which we never know. In this case, of course, you know it, but in reality, you never know what is in the truth. And you can see that these are possible sample average values. So these are average values of a sample of size 10. Now, if this is our null hypothesis, this is sample size, and this is the significance level. How often the null hypothesis will be rejected in this case? Or we can say it in other words, how likely the null hypothesis will be rejected? Well, let's think how we reject null hypothesis, right? Because it's a right tail test, you can see this is the null hypothesis. So alternative hypothesis, it means mu is greater than 20. Greater, it's a right tail test, right? Greater is a right tail test. So in this case, we will reject null hypothesis every time t-score will exceed a given threshold, right? And we can compute this threshold by using qt 0.95 and 9 degrees of freedom, right? So that's exactly, you have 0.95 here, you have 0.05 here because your significance level is 5, and that gives you 1.83. So every time our t-score exceeds 183, we will reject null hypothesis. But how often it will exceed, the t-score will exceed 183? Well, in 5% of the cases. We self-define this, right? This alpha, it's exactly how often we will reject null hypothesis because the t-score is too large. Also, it's still possible because if this is true, it means that all these average values are possible. So this is the average value that corresponds to this t-score in this particular case. And then it means that every time you have average value here, here, and here, and we know it's possible, we will reject null hypothesis incorrectly. So we'll make type 1 error. So what it means? It means that the alpha is exactly a chance to make type 1 error. So chance to make a type 1 error, you define yourself. And that's why I said before, try to make alpha as small as possible. Never more than 5%, never more than 0.05, but better in many situations you can use 0.01 or even smaller because you will reduce in advance, you will reduce chance to make a type 1 error. Here is an example. If I use alpha 0.01 instead of 0.05, you can see that, let me show you, this is 5%, 1, 0.05, 0.01. So you can see that the chance to make type 1 error will be reduced, right? So from 5 to 1%. So it's 5 times less type 1 errors you can make, right? So that's it about type 1 error. So type 1 error, it's incorrect rejection of null hypothesis. So it means that null hypothesis is true, but you reject it. Depends only on one thing, it's a significance level. And to remember, significance level, it's something that you define yourself in the beginning, so before you actually take a sample. And it means that the smaller alpha s, for example, if you use 1, 0.01, or 0.001, then the smaller chance for type 1 error will be. So if alpha, for example, is 0.05, it means that in 5% of all tests where null hypothesis is true, you will make a wrong decision. And then if alpha is 0.01, then it will be reduced to 1%. Okay. We didn't discuss which null hypothesis to use, right? So the selection of null hypothesis depends on many situations. But in science, very often, especially when you compare something, like if one medicine better than the other medicine, or for example, if one particular method for cleaning water is better than the other method, in many cases, we have null hypothesis as no effect. It means no difference. Medicine doesn't work, treatment doesn't work, and so on and so forth. From that point of view, the rejection of the correct null hypothesis means that you will give a hope. So it means that you will invest to this medicine, although it doesn't work at the end, you will find out. Or you will invest to a new treatment method, for example, water treatment method, but it doesn't work as well. So this is quite risky. So therefore, reducing the chance for type 1 error can be a good idea. In the next video, we will talk about type 2 error.